Okay, so it looks like we're on a good point to start. All right, good afternoon, everybody. My name is Illya Chekrygin. I'm a founding engineer at Upbound. I'm also lead maintainer on Crossplane project. It's an open source project we started at Upbound about 8 months ago. And we open sourced it right before KubeCon in Seattle last December. And today I want to talk to you about extending Kubernetes to orchestrate and support resources managed by public cloud providers. All right, so over the last decade, we have witnessed the emergence of cloud computing as predominant IT paradigm. Cloud computing enables organizations to focus on their core business competencies and quickly respond to changing demands without expending significant resources on infrastructure and maintenance. Organizations can instantly take advantage of the world-class services across infrastructure, and they can do so with scale their businesses globally with efficient pay-per-use model. Yet despite its predominance, the cloud computing remains completely under control of a small set of cloud providers. Amazon, Microsoft, and Google are at the front of the race and compete aggressively for market share and talent. And while these providers themselves are heavy adopters of open source technologies, the cloud computing remains predominantly proprietary and closed source. Each cloud provider offers a walled garden of proprietary services that are designed to lock in and keep the customers and maximize utilization of this specific cloud provider infrastructure. And while your own services, when you write your services, they typically run in VMs, containers, service functions, or otherwise portable, more frequently they depend on platform resources like databases, message queues, big data, AI, machine learning, and so forth. The very resources that cloud providers offer as a managed services. And what makes managed services so appealing is that you don't have to worry about a lot of these tasks like provisioning, deploying, scaling, doing disaster recovery, backing up. In other words, all the tasks that are required to run production-grade services. The cloud providers, they will take all responsibility for all those tasks, and they even give you SLA to guarantee uptime and delivery of your own services. In return, you will pay typically above and beyond to what normal hosting charges are. And effectively, you could run the same services yourself on the same cloud provider and save some money, but that additional markup is proprietary, specifically for the managed services, or for managing those services. Typically, when cloud providers adopt open source technologies, they will offer the same services. For example, right here you will see MySQL offered virtually probably by every cloud provider in some shape and form. However, the service name and wire protocol could be the only common thing. The way you provision, scale, and maintain that service could be specific for a given cloud provider. And when you look at an overlapping set of services provided by different cloud providers, you can understand why there is ever-growing demand for being multi-cloud. And what is missing, a control plane that spans across multiple cloud vendors, and what is needed is the way to manage workloads and resources in uniform and consistent way across multiple clouds. So we're at KubeCon, so I'm going to still do a quick intro to Kubernetes in case not everybody very familiar with Kubernetes. Just a brief couple of slides. Probably not necessary, but anyway. So Kubernetes is an open source container orchestration system for automating application deployment, scaling, and management. It was originally started on Google in June 2014. And actually this month we celebrate 5th anniversary of Kubernetes. Quickly, within a month, other big companies like Microsoft, Red Hat, IBM, Docker, they joined Kubernetes community, and community grew at exponential rate. They had first major GA release in July 2015 together with CNCF partnership announcement. And in a short 5 years, Kubernetes became de facto the platform to run containerized workload and services. It also achieved an amazing adoption rate among cloud providers. It became virtually ubiquitous today. Every major cloud provider offers Kubernetes as a service. With the latest one was adopted from AWS Web Services. They offered EKS in 2018. So clusters themselves became just yet another resource like a MySQL database offered by all major cloud providers. And again, similar paradigm. While provisioning them easy, but those provisioning steps could be very specific for given cloud provider. The way provision JKE could be different, slightly different, or a lot different from the way provision EKS or AKS. So needless to say that Kubernetes is a pretty incredible product. It revolutionized the orchestration of containerized workloads and services. And when I started using Kubernetes in 2015, I was sold on the idea. At that time, all I kind of knew and cared about was running containers, services inside the containers. It took me some time to realize that perhaps the best feature of Kubernetes is Kubernetes API. With its declarative style, so when user express what they want, in other words, desired state of your system, versus imperative style API saying that this is the steps I want to use to achieve that state. It is level-based, which enables robust behavior even if you miss in some intermediate state changes. It is complete and authoritative, and most importantly, it's extensible. And last part is very important because this, in fact, that what I've been doing for the last couple of years. I was working on the extensibility of Kubernetes, and I was writing Kubernetes in native applications. So how do you extend Kubernetes? So any programs that reads and write from Kubernetes API can provide useful automation. And there is a specific pattern for writing those programs, that pattern called a control pattern. Controls typically read object from Kubernetes API, perform some operations, and then save either the state of operations or state of an object back to Kubernetes API. Custom resources are extension of Kubernetes API. And Kubernetes application combined with custom resource definition, or CRD, together. Basically, Kubernetes application is CRD combined with the controller. And operator term was, if not invented, was introduced by CoreOS company, and it was a method of packaging and deploying and managing Kubernetes applications. The operator format gives software developer the template, which will tell Kubernetes how to deploy and manage the application. And there are several frameworks to choose to author your operator. Most popular of them, Operator SDK and Kube Builder, are based on the controller runtime. There are many few others, some of them very similar, some of them different, like Meta Controller, I believe there's Bash Controller, and of course you can use Client Go yourself, very low level library to author your own operator. In other words, writing from scratch. So if you look in basic structure of controller pattern, it's kind of continuous operation, continuous loop, which basically retrieve the object from Kubernetes API, compare the spec of an object to actual system state. If they're the same, maybe there's nothing needs to be done and continue. Otherwise, if there are any differences, perform some steps to bring the actual state to a desired state and save results into the object status. So when you write an operator, typically you extend Kubernetes types. So for example, the most common pattern will be my operator will create additional deployments or stateful sets and has custom logic to do something additionally which you normally would not do with the Helm installation. In other words, you do something active lifecycle management. So operator will read from API and create those Kubernetes types typically in the same cluster. And it's all kind of deployed in one cluster. And where that pattern became very useful is in the doing stateful set applications. Specifically, those applications which require some kind of data management. In other words, what started with, I believe, with CoreOS was etcd operator, Prometheus operator, and then Rook operator. In other words, all of them dealing with some additional data state, which normally you need to either some user knowledge to do manual steps. They kind of basically encoded them in operator logic. And that pattern started growing pretty rapidly. More and more independent vendors now package the applications with this operator format. And moreover, as you can see, that there could be multiple vendors or multiple projects dedicated to the same operator. Today, if you look in MySQL operator, you will see like up to 5, or probably even more right now, types to author or people who author the MySQL operator. And nowadays, it's almost easier to name open source technologies which offer a stateful set solution or stateful applications for Kubernetes who don't have operator, basically. If you go to a resource like, operatorhub.io, it's a pretty good resource where you can actually list all the operators. Gradually, you can actually select by level area of domain area right here, and you can see them all. It's not the only place. I also recommend to go check out the awesome operators. At the end of the slide, I have a reference link, and the slide is also available on the website of the scheduler, Kubernetes KubeCon scheduler. So check out this last slide. It has reference to all links. So now, if you can provision your stateful services, in other words, run your MySQL database as an operator in Kubernetes, it kind of tempts this question. So do I really need to use managed services from cloud providers? Do I really need to use RDS from AWS or Cloud SQL? And this notion has very appealing aspect. When you run your data and database services in the same Kubernetes cluster, you ultimately have this ultimate portability. When you run stateless service, you can run it anywhere. You can run it on your laptop. You can run it in any Kubernetes cluster, anywhere, in Minikube, GKE, on-prem. And it's easy because it's stateless. Once your state get involved, now you decide what to run it. However, if you put your stateful applications also on Kubernetes, ultimately you have this portability. You can run it as well anywhere. However, this thing has while ultimate portability is a goal, it has some problems as well. Some of them temporarily, some of them can be maybe long-term. For example, not all operator applications are very mature in the sense that even frameworks themselves, like control runtime, may be not exactly mature today. So they're still evolving. Other things that when you deploy your stateful application, you still don't have this unified console like managed cloud providers offer you, like where you can go and see all your stateful services at scale in one glance. So kind of you can either develop your own dashboard per individual services, but in fact, there is not one unifying dashboard or console. You're still on the hook to providing all the support and SLA for that operator. And that is the important part, because just because it's easy to deploy stateful set as an operator, it still does not absolve you to knowing what the stateful set is doing. So in other words, you still need to have domain knowledge of this given service. And sometimes it's a little bit more than if you run, let's say, in the cloud provider, because cloud providers themselves take some responsibilities for doing that, for doing all those tasks I mentioned earlier. Excuse me. So what happens is that we can actually take the same operator pattern and we can extend it not necessarily only to Kubernetes types. We can take operator pattern and extend it to types outside of Kubernetes. So for example, just like I can use operator pattern and create stateful set for MySQL using Kubernetes API, I can take the same concept and use cloud provider API and cloud provider SDK libraries to provision services on the cloud provider. So instead of doing MySQL in cluster, I can run MySQL in AWS using AWS provider API library to schedule and set up RDS instances, or Cloud SQL, or MySQL Azure. And with exactly those goals in mind, we started and introduced the Crossplane project. As I mentioned earlier, we open sourced it right before the KubeCon in Seattle last December. Excuse me. And the Crossplane is multi-cloud control plane. A single Crossplane enables provisioning and full lifecycle management of services and infrastructure across a wide range of providers and regions. Crossplane presents declarative management style API that will cover a wide range of portable abstractions, including databases, clusters, buckets. That's what we initially started. Since then, we added Redis clusters, and we're working in adding more and more resources. And Crossplane based on declarative resource model of Kubernetes. And it applies many concepts from container orchestration to multi-cloud workload and resource orchestration. Crossplane runs atop of Kubernetes, and atop of Kubernetes and leverages cloud provider infrastructure. Crossplane extends Kubernetes API via customer source definition. In other words, Crossplane is an operator. And each managed resources is represented by dedicated CRD. So today we support 3 cloud providers, AWS, Azure, and Google. And we support, as I mentioned already, resources like relational databases, Redis memory caches, clusters themselves, and buckets. In addition to managed resources and providers, Crossplane has notion of the resource classes and resource claims. So let's take a look at the cloud provider as a resource. Here's an example of defining cloud provider YAML for Crossplane. You can see it has two parts. First part is the secret, which contains cloud provider credentials. And second part is the provider, which has a reference to that secret and maybe have additional metadata, like in this case, it's AWS, it has a region information. Now, each cloud provider has a CRD, and it has also a dedicated controller, or may have a dedicated controller, which will perform additional provider validation. Similarly to provider, Crossplane represents every single managed resource by a dedicated CRD. Each CRD is strongly typed using cloud provider API for that resource, and we try to kind of model it after the cloud provider API. And each type has a dedicated controller, which is responsible for provisioning, validating, and once a resource comes up and become available, for generating connection secrets so it can be consumed from the applications. It's also responsible for tracking the status, and if it's diverged from declared state, it will attempt to make adjustable states, just like similar in Kubernetes when you create a deployment. You run, let's say, tell deployment run with 3 pods. If, let's say, one pod died or service node died, Kubernetes will automatically schedule new pods. So similar to that, it will attempt to do the same active reconciliation against resources. So if something changed in the resource, it will try automatically next reconcile loop to ratify and make sure the changes match into declared state. And this is the example of MySQL server in Azure provider. Notice that it has pretty much the property set. It's not a complete property set, but effectively which matches Azure API. So in addition to cloud providers and managed resources, Crossplane presents clean separation concerns by introducing, as I mentioned earlier, resource classes and resource claims. So developers, when I'm as an application developer, I typically don't really care what MySQL instance I'm using. Squint, sometimes I do care. But anyway, if I'm writing my application, let's say WordPress, and it needs to consume MySQL, I really don't need to know it comes from the AWS RDS or from Cloud SQL or from somewhere else. What I do care is the connection string and credentials, so I can connect to it and my application can perform its business logic. Now, you as a cloud or cluster administrator can use classes which modeled very closely or inspired by Kubernetes storage classes and storage claims. You can model resource class, providing all this metadata needed to provision resource. And claim can be now slimmed down and have very limited information. So for example, here's this class for standard Azure MySQL. If you notice, it has very similar properties as a raw resource, which we'll look in a couple slides back. So right here, this is the actual resource, concrete resource MySQL server, and this is class for that. So they're very similar in terms of completeness of the properties. Now, if we look on the claim for this resource, it now has a very limited information. In fact, it only has a class reference and potentially now has the engine version for MySQL, which I want to use. So it has a very powerful concept. Now, I'm as an application developer can use this claim and say, hey, give me MySQL in this cloud provider with the engine version 5.7. You as a cloud administrator can define what it means to provision MySQL in AWS, for example, or in Azure with all those properties. So it kind of creates two interesting notions. First of all, it has separation of concerns. I don't know all these details of infrastructure. Moreover, I don't know the credentials to provision those resources. Those could be stored away in the protected namespace, let's say a Crossplane system namespace, to which I'm as application developer don't have access to. So I cannot simply go ahead and provision any resources nilly-willy. However, Crossplane will understand the claim and will match with the resource class and provision and fulfill this request, return me back the connection secret. Okay. Let's look at the next slide. Yes, so now I can model my application in similar fashion. This is just mock-up example. Otherwise, it will not fit on the screen. But on top, I have my claim, a MySQL claim, saying, give me MySQL engine version 5.7. And this is a WordPress deployment, which will consume that claim. And in this case, the MySQL instance would generate the secret with the same name, which now I can mount in my deployment and now consume credentials, username, password, even connection string from it, using them as a properties, for example. Where are the properties? Somewhere there. Yeah, somewhere here. So now, if you look at this YAML file or manifest for application, if I were need to deploy this against, let's say, a different cloud provider, let's pretend that it was defined against Azure and I decided to deploy it against AWS. Very little need to change in this YAML file. I'm, as application developer, in fact, may even use the same class name if they were defined in abstract names. You, as a cloud administrator, now need to furnish all the resource classes for the cloud provider. So now you can actually define classes for as many cloud providers as we support, and I can apply exactly the same manifest file and provision my service without any changes. So that actually creates this very powerful concept of portability of my application. Now I can run and deploy it in any cloud provider without changes to manifest itself. So if that would be not enough, so there's more to that. In addition to cloud providers, resources, resource classes, and claims, Crossplane provides definition and support for workloads. So what Workload does is basically bring this all together. So now in one concise document, I can define my payload in terms of deployments or services, what I have to, my resources, and string it all together. And since I mentioned earlier that Crossplane is capable of provisioning Kubernetes clusters, now I can run Crossplane and a thin Kubernetes cluster, let's say in my laptop and Minikube. And I define workload of the WordPress application. And I can provide credentials to my Crossplane, say for AWS, Google, and Azure. And I say, go ahead and deploy it. And what can happen if that Crossplane will say, oh, I need to find a cluster where to put this workload. Well, I don't have any. So go ahead and schedule one. And it actually can figure out which to schedule. Today, Crossplane supports direct scheduling through the indication, okay, schedule not cluster. Specifically, you will have to provide cluster selector. In the future, we can have a cost-based scheduler. In other words, we can say, oh, where's it cheaper to run my WordPress today? Which cloud provider gives me better price for managed database? Deploy it there. Moreover, if you run in conjunction with other applications, you can use affinity, anti-affinity, and say, what is the best proximity or latency to deploy my applications? And Crossplane will fulfill that. And if there is no matching cluster, it can go ahead and provision one for you. So in December in Seattle, I did the demo. And you can still find it on YouTube, where basically I use this concept. I provision Crossplane using the same YAML file across 3 cloud providers and run the WordPress deployment across it. So I started with only Crossplane on my laptop, and I end up with the JKE, EKS, and AKS, and 3 managed database providers like RDS, Cloud SQL, and MySQL Azure, and deploy the WordPress application to 3 target clusters, all from scratch, just only providing credentials for the cloud provider. So Upbound mission is to create a more open cloud computing platform. And at the heart of every cloud is a control plane. And we hope that Crossplane could become the control plane for open cloud. With open control plane, anyone can add new API and extend to manage any open source or even commercial resources. Okay. So we are at the very beginning of our journey. Upbound is a very young company. We started about January 2018. So Crossplane is a very young project as well. So I encourage every one of you to come on GitHub, go on GitHub and check out and go through the examples. We have a lot of walkthrough examples from the WordPress, from specific services, or even GitLab example where we can run complete enterprise-grade deployment of GitLab in cloud providers of your choice. In fact, GitLab partnership was very important for us. We kind of working closely with them as a real-world application example to vet and prove our design concepts and constructs in Crossplane. With that, again, check it out, give us your feedback, submit PRs, open issues, and it was a privilege to talk to you today. Thank you very much for your attention. Okay, open floor for questions. I guess we have time for Q&A, so if anyone have questions, go ahead.
Thank you for your presentation. I can see you can create deployments to a destination cluster. How can you schedule your deployment among these clusters, such as 2 clusters or 3 clusters?
Right. So today, Crossplane supports the scheduler through cluster selector. So in your workload, you will say select cluster based on the criteria. So just like in the common label selector, you can say select where provider equals AWS, for example. So you will actually have to specify. That's the way it works today. You can, or even you can say if you name your clusters, not exactly as cattle, you can say deploy in that green cluster. Tomorrow, in the future, you can say, okay, find the cluster where cheaper to run. So you can create schedule. We work on the creating of schedule which can be cost optimized. Find the cheaper cluster to provision this workload. So in other words, if I'm using Redis database, the cluster, which cloud provider gives me better rate or lowest price to run Redis? Then you can actually put your workload in that cloud provider.
Okay. So from now, so we can schedule our deployment of among 2 clusters.
No, not today, exactly. So I think what you're asking maybe more closer to federation type question. Yes. Okay. Yes, while Crossplane workload scheduling is similar to federation in the sense of propagation, we shared a lot of concepts and we kind of learned lessons from federation, how to propagate our resources. The model is slightly different. In federation, you will have a control plane where you deploy your resource here and it will be propagated based on your labels, annotations, or templatization to Crossplane have slightly different objective. We're saying that we're not going to do propagation to multiple clusters. We'll have specific cluster deployment only. Because again, right now, we're not pursuing yet the model where we're going to have one application instance distributed across multiple clusters. Because that involves also solving the networking layer underneath that. In other words, when I deploy my WordPress in Google Cloud and AWS, I want to make sure that they can use the same database. Or something like that. So that's a little bit more challenging problem to solve. We work in that, and probably in the future we can have something analogous to that.
Okay, yeah, I see. Thank you. Thank you very much.
Any other questions? Oh yeah.
Okay, first thank you for your introducing to this awesome project. So I think my question you had answered some just now, but I want to get more information about how you manage the data, manage and sync the data between the cluster, as you know.
Right. So exactly. So this is very similar to the sense, not maybe from perspective of propagation, but yes. So when we schedule the databases in different clusters, data right now not going to be synced. And if you want to do that, you probably need to find your technology provider which allows you this global multi-cluster data syncing. Because again, it's involving solving network problem. In the future, potentially, if we have more solutions towards how to, let's say, punch the VPN hole between 2 VPC clusters, we can do something like that, but we don't have it today.
And another question is, so I think we will enhance it in the future. And do you have plan to define the PV and the PVC and use it across the cost?
Oh, that's a good question. Well, we're not really in the domain of solving storage technology. However, Upbound founders are the same people who started Rook project, which is very close dealing with the actual storage providers for Kubernetes clusters. So in the future, we can provision Rook-enabled cluster, which have different storage backends, cloud-native backends. So that's, again, that in the works. So we don't have anything right now.
Thank you.
Questions? Any more? Okay.
Hi, I have a question. When you install in the first place Crossplane, you will install that in a Kubernetes cluster. That means that you've got one Kubernetes cluster that is not part of your
that's correct.
Crossplane. Okay.
Yeah, that's you can potentially reuse the same cluster deploy workloads as well. Kind of similar with federation, where you share the same cluster as your control plane cluster. But ultimately, you probably want to select cluster which has very limited permissions. Because typically when you deploy your application, it implies some level of elevated credentials or permissions in that cluster. So what we typically recommend right now is to have a very lean cluster. We have a clean separation concerns, which namespaces can be used by application developer, which namespaces can be used by administrators. how propagation happens into some other clusters, where you can have totally different RBAC setup. Maybe not even giving anybody access to that altogether, or maybe different level of access.
Thank you.
Sure. All right. Well, thank you for your questions, guys.